about the sine graph and what it looks like. So that anytime you see this function, y equals sine of x, what does that graph look like? Just like we've learned this year about linear graphs, y equals mx plus b, and quadratic graphs, y equals x squared, and polynomial graphs. You know, we're just learning about another graph, right? Another kind of function. And just like all the functions we've learned about in the past, we're going to talk about domain, we're going to talk about range, we're going to talk about symmetry, we're going to talk about how to transform it, up, down, left, right, skinny, tall, fat, whatever. All of the things we've learned about all the functions we're also doing with these trig functions, okay? So it will feel like you're back in pre-calc a bit here. Okay. So I had you go through and find these numbers. Just quickly, will you help me fill them in because I don't have them memorized like I should. 60 is like 0.87 or 86, which was closer. Okay, 87. Okay. 90 is 1, correct? Then the numbers should go back down, although because all students take calculus, sine is positive in the second quadrant, which means even though the numbers start going back down, they remain positive, because it's as long as we're in the second quadrant, correct? Now you might have noticed that I kind of started skipping numbers. I didn't fill them all in between because I figured you would kind of get the idea. So 120 is a 60-degree reference angle, and because all students take calculus, sine is positive in the second quadrant, that is simply a positive 0.87, just like 60 degrees was. And 135 will be a 0.71, just like 45 degrees was. And 150 will be a 0.5, just like 30 degrees was, because those have the same reference angles, correct? And 180 will be 0, just like 0 is, okay? But then when we move to the next quadrant, quadrant 3, tell me about sine in quadrant 3. Negative. So now, and I've kind of not done all the numbers in between like I did here, so now realizing that you're skipping your 30s and 60s, I just did the 45s and 90s. So the 45-degree reference angle is 0.71, but because it's quadrant 3, it's a negative 0.71. 270 has the same reference angle as 90, but because it's quadrant 3 and quadrant 4, it's negative. 315 is quadrant 4, so it has a negative ratio. 360 is back to 0, and then 390 is back to 30, so it's just 0.5 again. And what happens past 360? If we keep going, can we keep going infinitely forward and infinitely backward to negative angles? What's going to happen? It's going to repeat over and over and over for every time we go around the unit circle. Okay, so thus this is a periodic function. And let's graph this and then talk about what the period is. Okay, so 30 is 0.5. 45 is 0.7, that should be 7.5, so we'll guess it's right there. 60 should be 0.8 something, so we can just kind of guess it's right there. 90. Anyway, you should end up with a nice, lovely wave curve. Correct? Is that what you got? Yes? Okay, so now let's look at the graph to analyze these details that we want to know about this function here. So at this point, if you want to, you can use the graph you created on this paper. So why did I have you do 2? Why 1 on this paper and then we're going to transfer it and go ahead and put it on the card? Why would I bother doing it twice?
We learn by repetition.
Okay, there's a good reason. What else? This was just in case you were writing in pen and made mistakes the first time around. So that way when it's on your little card to put with your notes, hopefully it's accurate. Do you know what I mean? Okay, so let's look at the important points here. Also, I did this one in degrees and I did this one in radians. We're going to do both, but I think you need to get most comfortable with graphing in radians, honestly. Okay? So pi halves is the same as 90. That's where our graph goes up to 1. Pi is the same as 180, so it's at 0. 3 pi halves is -1. 2 pi is +1. 5 pi halves would be back up to 1 again. If we go the other direction, negative pi halves would go back down to -1. So you should have this sine wave that just continues to repeat. Correct? Okay, so let's talk about all these important details that you're going to need along the way in this chapter. Symmetry. So we have odd functions and we have even functions. Odd functions are where you can turn the graph upside down. It rotates 180 degrees and still looks exactly the same. Even functions are where you fold it across the y-axis and it looks exactly the same on both sides. So symmetric to the origin, it just reflects upside down. Symmetric to the y-axis, you can fold it and it's the same on both sides. Which type of symmetry does this one have? Did someone say all? It's either odd or it's even. It can't be both. It's odd, yes. So odd means it has origin symmetry, correct? So that for these numbers over here, when x is positive, y is positive, and it reflects so that when x is negative, y is negative. That type of idea. Okay, what's the domain of this function? What x values can we plug in? Very good. So there's many ways you can write that. You can write it, just write out all real numbers. You could write a fancy r with a double stem. You could just do negative infinity to positive infinity. Whatever's going to help you remember that the best. Of course, we typically use this a lot. So, okay. Range. What's the range? Is it going to be closed brackets or open parentheses? How is that going to be written? Brackets, because it actually does get up to the point 1 and -1, but it does not go past those. So range is -1 to +1, or that could be written as y, like, you know, in set notation. This is interval notation. You could also write it in set notation, which would be like -1 is less than or equal to y is less than or equal to 1. Correct? That means the same thing. Okay. Period. How long is the graph before it starts to repeat again? What's the distance? Okay, I'm hearing one person giving me the answer there. I heard it again. 2 pi is the length of the period. That's how long the x value is before it repeats again. Or what's another way of saying 2 pi? 360 degrees, either one. Be familiar with that. Okay. Key points. Okay, at some point when you're graphing problems like this, they are going to ask you to list and graph and label the 5 key points for your graph. The 5 key points are your 3 intercepts, your maximum, and your minimum. Okay, that's what the 5 key points are. 5 key points. If you want to write the number 5 so you can remember that there's 5 of them, that's fine, but it is going to ask you that on stuff that you're doing. Okay, so intercepts. Where are the intercepts for the sine function? 0, 0, right? Where else? Yep, over pi and 0. Okay, and where else? 2 pi and 0. Good. Okay, now we have a minimum value that's a key point, and we have a maximum value that's a key point. So where's the minimum of this graph? 3 pi halves, comma, -1 is the minimum, right? And where's the maximum? Positive pi halves and +1. Okay. So this is your basic sine function. What if you did something to it, like stretched it vertically or compressed it horizontally or transformed it up or down or left or right? What's going to happen to those 5 key points? Some of them might change depending on what's happening, what's transforming, okay? We're going to talk more about that in section 2.2. Today we're not going to do a lot with transforming. 2.2 is more where we're going to deal with like phase shifting, moving it left and right, okay? All right. Oh, okay, I do want you to be aware of one thing. So what is the amplitude of this graph? We should talk about that really quick. I should have put that on here probably. What's the amplitude? Do you remember the definition of amplitude? Half of the distance from the top to the bottom. Here's the very bottom point at -1. Here's the very top point at +1. What's half of the distance between the very bottom point and the very top point? +1, right? So for this particular problem, we should just write this in here somewhere. I don't know where. I should have put it in, sorry. Amplitude. My handwriting is lousy and I don't want it to be. Okay, amplitude equals 1. Okay, now sometimes your graph will go upside down if it has a negative in it. We'll talk more about this just in a second here. But does that mean that the amplitude is -1? No, amplitude is a distance. So amplitude is always, always positive. I don't know where you need to write that, but amplitude is a distance, and so therefore it is always given as a positive number. All right. Before we go to cosine, let's go ahead and I want to just talk about the amplitude a little bit more. Here's your standard form for well, we'll add more to this on another day. But if you were to do sine, yeah, let's just do this much of it. My lead just. What's our time? Oh, crap. I just realized that. Dang it. Okay, so a sine x minus c. What's your guess about what a and c do? Any ideas? A is the amplitude, and it will stretch it, correct? If you put a negative here, does that change the amplitude to a negative? What does it do? It just reflects it upside down. Okay, and then I heard someone say what they thought C would do. C is something we already learned called the phase shift, and that will move the graph left or right, the opposite direction. Okay, so if I do y equals -2 sine alpha, let's just keep it as x, although sometimes, quite frequently, they might put I'll just go ahead and put a theta there instead of an x. Is that okay? Does that throw you if I use a theta instead of an x? Don't we often use Greek letters for the angle? And isn't that what that is a Greek letter for the angle? Yes? Right? But it still means it's just the domain. It's still x, even if it's theta. It's still relatively the same thing on your graph, okay? All right, so this would mean our amplitude is twice as tall as it would normally be. So let's do these critical points like pi and 2 pi. And then our graph, instead of going up to 1 and down to -1, what does this -2 do to it? It's going to change that amplitude so that it's going higher and lower. And then what does this negative do to our graph? Flips it upside down so that this graph would look something like this instead. Do you get the idea? Do you see how this is just the same types of things we've talked about with other functions? Okay. If you want to go through and fill in these details on your own and just prove to yourself that what I'm going to show you is true, that's a great idea.